All right, let's just jump right into this. When most of us watch ski jumping, we see these athletes shooting down a massive snowy ramp and soaring through the air. But what you're actually witnessing isn't just falling with style. It's this highly calculated, precise orchestration of physics, aerodynamics, and honestly, superhuman biomechanics. Welcome to this explainer, where we're going to break down exactly how the human body manages to temporarily defy gravity.
Just think about the sheer scale of what we're dealing with here. We are literally watching humans act as unpowered aircraft, defying gravity at dizzying heights over these breathtaking mountainous backdrops. I mean, it looks like magic or maybe sheer madness, but every single fraction of a second is governed by intense scientific principles.
So, to understand how this is even physically possible, we'll break it down into 5 quick parts: the 4 phases of the jump, the in-run and explosive takeoff, the V-style revolution, aerodynamics and wind impact, and finally, mastery of the human body.
Part 1. The 4 phases of the jump.
Every single jump follows the exact same foundational roadmap, cleanly divided into these 4 chronological phases. First, you've got the in-run, where the athlete accelerates. Next, the explosive takeoff, right at the edge of the ramp. Then, the aerodynamic flight phase, where they actually glide. And finally, the controlled landing to absorb all those massive impact forces. We're going to pause time at each of these crucial junctures to uncover the hidden science at play.
Part 2. The in-run and explosive takeoff.
Okay, so we begin at the top of this massive 35 to 37 degree ramp, and right away, the battle against aerodynamic drag begins. By utilizing this intense crouch, known as the perfect egg position, where they keep their torso almost perfectly horizontal and their knees flexed exactly at 90 to 100 degrees, the athlete shrinks their frontal surface area to less than half a square meter. By tucking their head in with this meticulous posture, they slash aerodynamic drag by 30 to 40% compared to just standing upright. And they absolutely need that lack of drag, because in just 5 to 7 seconds, gravity acts as the ultimate accelerator. Thanks to an incredibly low friction coefficient between the skis and the snow, the jumper gets pushed to a blistering macro speed of up to 100 kilometers per hour by the time they reach the very end of the ramp. But here's the crazy part. At that extreme velocity, moving at nearly 28 meters every single second, the athlete has a micro window of just 0.3 to 0.4 seconds to actually execute their explosive takeoff. If they're a fraction of a second too early or too late, the entire jump is completely compromised. This kinetic sequence fires in a rapid chain, going from the ankles to the knees right to the hips. According to biomechanical motion data captured by Kinexa, this movement unleashes up to 2,000 watts of mechanical power. That generates a vertical force of 2 to 3 times the athlete's own body weight, launching them at this optimal 10 to 12 degree angle. And they do all of this in less time than it takes you to blink. Part 3. The V-style revolution. Now that we're airborne, let's take a quick detour from our timeline to talk about a massive paradigm shift that completely altered the sport. Jan Boklov. Pre-1985, every single jumper kept their skis perfectly parallel. It was just considered the only correct technique. But Boklov, who was essentially an underdog, accidentally discovered the V-style. At first, he was ridiculed and even heavily penalized by judges for poor form. But his empirical discovery kept resulting in longer jumps, and eventually the science caught up, validated him, and completely revolutionized the discipline. To understand why Boklov's weird style worked so well, we need to look at lift versus drag. These are the key aerodynamic forces defining flight efficiency. Lift pushes the athlete up, fighting gravity, while drag is the resistance pulling them back. Scientists realized that the V-style dramatically improved the lift-to-drag ratio, boosting lift by up to 30% while only slightly bumping up drag. It effectively turned the athlete's body into a highly efficient wing. Check this out. By spreading the skis at an optimal angle of 25 to 35 degrees and angling the body to form an aerodynamic arrow shape, the jumper creates a surface area that generates up to 600 newtons of lift that magically offsets 60 to 90% of the jumper's total body weight. The downward acceleration from gravity drops from 9.8 meters per second squared to as little as 1 meter per second squared. I mean, they aren't falling anymore, they are literally gliding.
Part 4. Aerodynamics and wind impact.
Let's move back to the flight phase. You might intuitively assume a tailwind pushing from behind would carry you further, right? Actually, no. A headwind is a ski jumper's best friend. Blowing directly against them increases their apparent speed, which in turn boosts lift by a massive 44%. A tailwind, on the other hand, is unfavorable and honestly quite dangerous.
It kills your lift and forces a much steeper, sudden drop. And to avoid stalling out while fighting these variable crosswinds, the jumper has to maintain absolute flight control. They manage their pitch, that's the front-to-back tilt, using micro-movements of their pelvis. They manage roll, the lateral tilt, using their hips and asymmetrical arm spreads. And they manage yaw, the horizontal rotation, with subtle shoulder shifts. These are tiny, almost invisible movements, because any sudden, sharp jerk will cause amplified oscillations and a total loss of control.
Part 5. Mastery of the human body.
Pulling off these micro-adjustments in midair brings us to the superhuman inner workings of the athlete's biology. As sports physician Dr. Christophe Delong notes, the neurological speeds happening right here are just mind-blowing. The vestibular system in the inner ear detects gravity shifts and stabilizes the athlete's gaze in just 7 to 15 milliseconds. Their proprioceptive system provides constant physical feedback at 100 to 200 hertz. This allows the cerebellum to automatically correct the body's posture in under 50 milliseconds. That's literally faster than conscious thought.
And get this, what's truly wild is that all of this biological computing happens while managing massive adrenaline and a heart rate pounding at 160 to 180 beats per minute. To execute this properly, the athlete has to enter a complete psychological flow state. Time literally distorts, conscious thought drops away, and their technique runs completely on autopilot, driven by thousands of hours of visualization and intense muscle memory.
So given the thousands of hours of intense training required to completely reprogram their nervous systems for these fleeting 15-second flights, you really have to ask yourself, are we simply watching elite athletes sliding down a hill, or have they engineered themselves into actual unpowered human aircraft? It's just a breathtaking intersection of human will and absolute physics. Thanks for joining me for this explainer, and I really hope you look at the sky and the slopes a little differently next time.